When we talk about atoms nowadays, we usually use diagrams like this, where we've got a nucleus in the middle of the atom that has protons and neutrons, and then there are electrons around the outside of the atom. But of course, we didn't always know that atoms looked like this. Scientists had to discover each one of the subatomic particles one by one, because of course the atom is so tiny that you can't just look at one and see what it looks like. Scientists had to do a whole variety of experiments to discover these various particles, as well as the overall structure and shape of the atom. So the neutron here was the last of the subatomic particles to be discovered, and we're going to talk about how it was discovered in this video. So, in the early 1900s, around 1910, 1920, this is what scientists thought the atom looked like. It's not too different from this version over here, except that there aren't any neutrons in the nucleus. Rutherford's gold foil experiment indicated that there were protons, positively charged particles, in a nucleus in the center of the atom. And then other work by Bohr and certain other scientists gave the idea that there were electrons spinning around on the outside of the atom. But no neutrons had been discovered yet. Now, there were a few clues that led some of the scientists to think that something like neutrons might exist in the nucleus of the atom. First of all, some scientists said, look at this. There are all these protons in the nucleus of the atom. Protons are positively charged, and like things repel, right? You've got two positively charged things, they want to push away from each other. So they thought maybe there is something else in the nucleus of the atom that helps keep these positively charged particles together, keeps them from just pushing away and repelling each other. And it turns out that is exactly what neutrons do. So that was one clue that neutrons might exist in the atom. Here's another. When scientists compared the masses of helium and hydrogen, they found some interesting things. Scientists knew that each hydrogen atom had one proton. Here, I've drawn them here. And they knew that each helium atom had two protons. They're the two protons. They decided that a proton should weigh 1 AMU, so they would think that two protons here would weigh 2 AMUs, and the two protons from here should weigh 2 AMUs. So 2 AMUs on both sides of the scale. But it turned out that one helium atom was still heavier than 2 atoms of hydrogen. And this didn't make sense, because they knew that there was an equal number of protons. It turned out that it took 4 hydrogen atoms to balance out 1 helium atom. And this didn't make sense, because here you've got 4 protons and only 2 protons over here. How are these things balancing out? Now, of course, you may already know the answer, although scientists back in the 1910s, 1920s didn't. And the answer is that helium doesn't just have protons in its nucleus. Many helium atoms have 2 protons and 2 neutrons. So instead of just having 2 protons, this helium atom has 2 protons, 2 neutrons. Now we have 4 particles that balance out the mass of the 4 protons on this side of the scale. So that's why it turned out that 1 helium had to be balanced out in weight by 4 hydrogens. But of course, scientists didn't yet know that neutrons existed. And here was one other thing that they also noticed. They could measure the atomic number of atoms, which is the number of protons in them. And again, they decided that each proton weighed 1 AMU. But then when they determined the mass of the whole atom, they'd find that it was greater than the number of protons. So here in helium has an atomic number of 2 protons, but its mass is 4 AMU. Where's that extra mass coming from? Lithium has 3 protons, but its mass is 7, 4 and 9, 5 and 11. So it became clear that there was something else in the nucleus that had mass and was causing the atoms to weigh more than you might expect based only on the number of protons. But it wasn't until a scientist by the name of James Chadwick came along in 1932 and he really figured out exactly what neutrons were. Here's how he did it. He took atoms of beryllium or boron or lithium and shot alpha particles at them, kind of the same way that Rutherford shot alpha particles at the gold foil in his gold foil experiment. So James Chadwick shoots these atoms with alpha particles, and he notices that rays get released from the atoms of beryllium, boron, or lithium. So something is getting shot out of these guys when they're hit by alpha particles. Now, it's not clear what's coming out, but one thing is for sure. Whatever is getting kicked out of these atoms, it doesn't have a charge. So it can't be protons that are getting shot out because they're positively charged, and it can't be electrons that are getting shot out of these atoms because they're negatively charged. So something that doesn't have a charge is getting shot out of beryllium, boron, or lithium atoms when they get hit by alpha particles. Okay, they still don't know what it is. But here's the second part of the experiment. James Chadwick and his co-workers put paraffin, which is just a fancy word for wax, like the kind of wax in a candle. They put a little sample of paraffin in front of these rays that are shooting out of these atoms. And they discover that when the paraffin gets hit by these rays, protons come, bam, they come shooting out of the paraffin. They come shooting out, and these protons get shot out really fast. So whatever is coming out of the beryllium, boron, or lithium is moving fast enough and is heavy enough to bang into the atoms of the atoms that are in the paraffin and kick out the protons. I want you to think of the protons kind of like pool balls. They're pool balls that are getting shot out of the paraffin, okay? And so at first they think maybe what's coming out of these atoms is something called gamma rays, which are made up of particles that are incredibly tiny and incredibly light. But the more they think about it, it doesn't make sense. And here's why. Because these pool balls, these protons, are getting shot out of the paraffin so quickly that it just wouldn't work if they're getting hit by gamma rays. Because the gamma rays are so tiny. It's like hitting a pool ball with a tiny BB and expecting it to fly away. Almost no matter how fast you hit this pool ball with a BB, you wouldn't be able to get it moving just because that BB is so light. Doesn't matter how fast it's going, it's just too light to be able to slam into the pool ball and get it shooting off. So they realized, no, it can't be something light. It can't be something like gamma rays. Instead, think about this pool ball analogy. If you want to get this pool ball really shooting fast, you got to hit it with something that's about the same weight as this. You can hit it with another pool ball going pretty fast, and that'll make it shoot off. So what they decide is that whatever is coming out of these atoms has to be about the same mass as the protons that are getting shot out of the paraffin. They know that the things that are getting shot out of these atoms don't have a charge, and they know that they have to be about the same size and mass as the protons. So this is how the neutron is discovered. It's neutrons here that are getting shot out of these atoms. You hit beryllium, boron, or lithium with alpha particles, neutrons come shooting out. They don't have a charge, so you get these rays of neutrons shooting out, and the neutrons then hit the atoms that make up the paraffin. They smash into the atoms that make up the paraffin, and then the protons come shooting out nice and fast because they've been hit with something that's just about the same mass as they are. So it really gets them moving. So that is how the neutron was discovered, and that then completed the idea of the atom as being made up of 3 subatomic particles: electrons, protons, and neutrons.